there are 4 hours of like contests every week, and then also 1 hour of lecturing. So these contests are custom made by our staff, and so they're like completely new problems you can't find outside, and offer a good representation of like the difficulty of the corresponding musical level. Along with that, for really high performing students, we offer grandmaster classes for students aiming for musical platinum, camp, or even IOI. Along with that, for students who are less interested in climbing to the highest levels in computer coding, we also offer APCS A series, and we also offer AI classes, and I think game design classes that we've picked up recently. Okay, with that being said, I'm going to just start explaining the problems now. So screen share. We pull up the problems. Okay. So problem one. Shrink everything down. Oh, okay. So this is problem one. So for the viewers, I hope everyone's read the problem statement, but I'll just quickly go over again. So we basically are given an n by n grid of cells, n is less than 2000, and we're guaranteed that n is even. So we basically first have we initially, like, Farmer John paints the cells into a formation where they're going to be symmetrical, both like vertically and horizontally. So it's like 4 quadrants. But yeah, all you can think about is basically we can flip it over both the x and the y axis, right? Like across the middle. That's basically what it's doing. And then Bessie comes and breaks some cells, basically, changing a lot of the cells. But now we want to the problem is then um find the least number of moves to turn the new canvas into the original canvas. But on top of that, we have an additional challenge, which is that we have like we have few queries or view queries in this problem, where for each query, like the canvas changes an additional time and turns from, each spot, it can either turn from an empty spot to a filled spot. And after every single one of these queries, we have to then again find how many moves it'll take for it to be symmetrical. So our first observation after this is, okay, so if we want it to be symmetrical, let's first we first find that, like, every single time we have a problem like about like symmetry like this, right? We want to find out like where each cell maps to like one another, right? So we see clearly that like this cell, this cell, this cell, and this cell, like if they're like, they all like basically if we reflect across, I'll make it more clear. So let's say like here, right? Here, 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 and here. These 4 cells can like reflect across to each other. So that means that these 4 cells have to be equal, right? So let's first find like a mathematical representation of what what operations there are. And we realized pretty quickly that, like, so if this cell is like, so the lines dividing this are like n over 2, both on the x-axis and also n over 2 on the like y-axis, right? We notice that if we want to get any number from like here to remap these numbers back to this one, right? All we have to do is, like, if we have ij, we see that if I is like greater than n over 2, right? We basically want to flip it over. So like if we like I is like the vertical one. So if I is like here, right? We want to like flip it over this horizontal line. And if you've done like geometry or math with coordinates, like the way to flip something is just you can do n minus I. Right. So this goes from here to here. And it's the same thing for j. So if j is greater than n over 2, right, we turn j into m minus j. So that's kind of the initial first step, because so now, right, we see that any points with like ij, right, we remap it back to its like original spot in the first quadrant. And we know that any of the 4 points that map to this one point all have to be equal. So when we see a problem like this, right, like, let's ignore the queries for now. Let's not think about queries. How will we do this for the original problem? Well, I mean, we can kind of see that, like, so if we know like every single point here remaps to like the original point, like original point here, the problem then becomes, we just want to find, like, out of these 4 points, the least number of moves it'll take for them all to be the same, because we need all of them to be the same, right? And we can just quickly do some casework, right? We see if this is like I'll just label them like 0, 1. So like dot equals 0 and then this equals 1, right? If we like quickly see that if we have like, 3 dots, right? So 3 0 0 0 0 1, right? Now obviously we should turn this one into a 0 instead, right? So that would just be one move. So if we have like, 3 ones, right? 1 1 1 0, right? Out of these 4, obviously this should turn into a 1. If we have like 4 or something, then we don't need any moves at all. But if we have like 2 and 2, 1 1 0 0, then it doesn't really matter. We can turn them either into zeros or ones. So let's just say for the sake of this one, we just turn those zeros into ones. It doesn't really matter. So this is a pretty clear solution to if we don't if we ignore the number of queries, the updates. If we ignore the updates, we have the problem solved, right? We can loop through all the points. We see which one it maps to, and then from there we want to choose the least number of moves to change the to make them all equal. They make the 4 points mapping to the one original point equal. Okay, but now we have to deal with the issues of queries. But we see that like if you've gotten to this far, right, the number of queries isn't really that much of a task because, right, let's say we have like what these 4 points map to originally, right? So let's say this is like originally this is like 0 1 0 0. Okay, we see that clearly here, right? Originally, the number of moves it takes to make these 4 equal is 1 move, right? We turn this one to a 0. But let's say we have done an update and now we like our update turned this bottom right 0 into a 1, right? Okay, so now what's the optimum number of moves? Now we see that it should take 2 moves, right? It should take 2 moves. But and like the number of like the time complexity of this, right, to figure this out is all 1, right? Because every single update, we only see 1 point changed. We see the point that gets changed. We see how much it took originally, and we just like compare it, right? So we see that these 4 cells originally took 1. Like after the update to 1, right? Now it takes 2 moves. So the entire answer is just a previous answer plus another move, right? Well, it can also go the other way around, right? So if we update this one now to 0, so now it's 0 0 0 1. Now the answer goes from 2 to 1 for these 4 numbers, right? So that means that the answer has decreased by 1. So we clearly see that the best way to do this is if we know the answer like of the original one, right? Answer here, we can quickly use what we've already computed to process this after this update in like basically linear time, right? Because we just have to see what it was originally, update it to like what like the new one, and then see how the answer changes, right? So this will get us a new answer. So like I'll call like answer. So this original answer was answer 0. This one's now answer 1, right? And we can build off answer 1 and do this query similarly in linear time as well. So this is answer 2. And that's pretty much all this problem like inherently is. Like there's nothing too challenging about it. It's so like I think the idea behind this problem isn't too challenging, but the implementation is a little annoying. So I'll go over some implementation details as well. So let me see. So my hint for implementing this is, let's say we instead of maintaining the whole quadrant, right? So we already did the thing where we reflected across each other, right? So instead of maintaining every single like the values and recalculating which ones like remap, for example, like right, we see that something got updated, right? Instead of recalculating where all 4 of these update each time, instead let's just maintain an array that stores basically the value of everything if they got remapped back to the first quadrant. So I'll call this the first quadrant, right? And we do these operations that we showed here, right, to remap everything to the first quadrant. And so every single and in the first quadrant, we basically store how many like for each spot, right? This spot corresponds to this one, the original one, also this one, but also this one, right? Because it's everything that can reflect onto this spot. And the number here is basically a number from 0 to 4, storing like basically saying how many are spots out of these 4 spots are filled. So if this is like 3, right? That means that we don't know exactly which spots are filled, but we know that like these, like out of these 4 spots, right? 1, 2, 3, 4. Out of these 4 spots, 3 of them are filled. And from this, like if we calculate this to begin with, right? We use this in the beginning. the first iteration, we just like do a quick check, and the answer is really easy to find, right? Because if it's 3, that means that it'll take 1 operation to make them all equal. If it's 2, it'll take 2 operations. If it's 1, it'll take 1 operation. 0 or 4, 0 operations, right? So we do this to quickly make sure and then every single time we update, right? If we update a point here, right? Let's say we update this. If we update this, all we need to do is see how this one changed. So if this was originally like filled, right? And we turned it to not filled, right? We see which point this corresponds to in the original first quadrant, which is really easy because we do these operations, right? So this corresponds to this one, let's say. Let's say this one originally was, this point was originally 4. So now we just, all we have to do is subtract 1 from here. Please read this one went from filled to not filled. So this one is now 3. We see that if this spot goes from 4 to 3, the answer has increased by 1. Because originally 4 is equal to 0. Now 3 takes 1 operation. So the number of operations it takes to maintain the whole thing goes up by 1. And so yeah, we just take the original answer and just add 1 to it. Yeah, that's pretty much this problem. Does anyone have any questions about this? No questions? Okay. So for the people who didn't get this, I'll go over some of the. I'll also go over the. I'll go over some of the like the test cases here. This the partials, right? So I hope everyone like Well, first off, like so you kind of had to make the observation that I was reflecting, but if you make the observation that I was like if you can calculate for one original grid, right? That means that you should be able to get it for these, right? Because the number basically for these time complexities, right? And less than 4, and also this one, right? For these time complexities, we're basically able to calculate out. We can like do an O of n squared we can do an O of n squared operation for every single like update, right? And these will still pass. So like basically like we saw how like we originally calculated it just by looping over everything in the array, right? That's the original way. So if you just knew how to do this and you coded it, this should have been able to pass these 6 test cases, right? Because the time they recalculate every single time is n squared. So if there's u updates, it'll be O of the u n times n squared. And so for n less than 4 and also for u less than 10, this passes. The full solution, everything else, my solution that I presented was O of n squared plus u, because it was n squared basically first to recompute to pre-compute everything for the original one, and every single update we can process an O of 1 time. So time point C is O of n squared plus u, which passes for everything else. But yeah, if you were just able to solve it for the original test case, you could get the first 6 test cases, which is still like they like 40%. Okay, if there's no more questions about this, I'll just jump into the next problem. Um, oh wait, the next one is just this one. Okay. So the next one is really short. So but it requires like you have to kind of to understand what a mex is. So take some time to understand. Yeah, like especially when you're in contest, like a good thing to know from this contest is like, yeah, don't get like even if it looks short, make sure you fully understand the problem before jumping into coding. So basically, the problem just gives us an array of n non-negative integers. So n is less than 2 times 10 to the 5th, right? And we want to we can change any element of a to any other in number in one operation. And the mex of a array is defined as the minimum non-negative integer it does not contain. So basically, if we have an integer that's like 0, 1, 3, 4, right? Mex equals 2. Any array that doesn't contain 0 is obviously like mex equals 0. because 0 is not there, right? So it's basically like, you kind of go from 0 to like whatever number, and then you just keep counting until you find a number that's not there. So that's basically just what a max is. And for this problem, yeah, the issue is that you want to find the minimum number of operations you need to make for like every I from the range of 0 to n, you want to make the max of A equal to I. Yeah, okay. So first off, we can kind of see that there should be a pretty straightforward like solution, like just that passes the first 6 sample test cases, right? The immediate like thought is, okay, let's just try to loop over I. So if we loop over I, so we just like, we loop over I, and then we want to find the number of operations to make the max of the array equal to I, right? So in order to make it equal to I, we see that, okay, we need to fill out everything that's less than I. So let's say like I equals 2, right? So then that means that we need to fill in 0 or 1. If 0, 1 already exists, then we don't need to do anything about that. But if any of 0, 1 are missing, we need to fill it in. That's just like, yeah, that just like makes sense. And in order to do that, right, let's try looping over the entire array and like finding, finding if 0 or 1 exists each time, right? That's pretty straightforward. So check if numbers less than I exist. So that's the first step. Next step is we see that if you can kind of see from the sample, but for example, if we want to do I equals 2 for the sample, right? 0 exists, 1 doesn't exist, we fill in 1. But the issue is now the array is now 0, 1, 2, 2. The max is still not 2, right? The issue is that, if we want the max of a number of the array to be equal to I, we also have to get rid of all the I's. Rid of all I's. Right. So the reason why the max number of operations to make the max 2 in this array is 3 is we have to change one of the 2's to 1's and then change these 2 to like anything else. So we can change those 0, 1, like 0, 0, something like that, right? And this will give us 3 operations, and this is the middle number. I hope after like seeing this, right, you can notice the observation that basically it's always optimal to do these 2 kind of together. So we always want to put I into turn I into like if we're missing, let's say we're missing 0, right? Or here in this test case, we're missing 1 in the original test case. We obviously want to turn a 2 into a 1 because we're kind of like doing 2 birds with 1 stone, right? We're just getting rid of I's, and we're also checking if numbers less than. We're also making it so that all the numbers less than I exist. But yeah, and from there, I think you should be able to make the observation that basically it's just whichever one is greater out of these 2 is the number of operations we need, right? Because if we are able to fill in all the numbers less than I in a really quick time, but we still have I's remaining, then that means that we still have to do the rest of the operations getting rid of other I's, right? So like just like in this sample case, if we're trying to make the max 2, we make the 1. There's only 1 number missing. We make the 1, but there's still 2 more 2's. So total number of operations is going to be 3 because we have to get rid of the other 2 2's. But on the other hand, right, if there's like not many of those I's, but the issue is that the numbers less than I don't exist, that means that we have to spend our remaining operations filling in the rest of the numbers. So for example, let's consider the sample, right? For the sample, if we wanted to process the I equals 3 case, like there's no 3's that exist, so there's nothing we need to turn into, like there's no 3's to get rid of first. So that means that all of operations just have to be spent on making the numbers that are less than I exist. So here we see that 0 exists, right? 0 exists, 1 doesn't exist. We have to spend 1 operation making it 1. 2 already exists. So these 2 exist, this takes 1 cost. So the total cost is 1, which matches the same. Okay, so the problem, yeah, so once we make the observation that the number of operations to do for each I is just going to be the maximum of these 2, right? Number less than I that don't exist and number of I's. the problem should be, we should be able to get these test cases really easy, right? Because all we have to do is loop over I, see how many numbers less than I don't exist, and then compare, see how many i's there are, and just find the maximum. And the time complexity of this is O of n squared, right? Because O of n to loop over it, O of n to check out of these, right? And so it's L of n times n equals n squared. Oh, right. Okay. So that's the first first six test cases. That should just be kind of apparent from from just doing a bit of casework and testing some problems. So now let's think about how we can get the whole thing. So the whole thing, we see that, n is 2 times 10 to the fifth. So we have to do the rest, other operations way quicker than this. And what we see that, so for n less than 10 to the fifth, that means that every single time we loop over I, like loop over I obviously still has to be in the final problem, because otherwise how are we going to print out everything, right? Like we have to find the answer for each I. That's just not, but so that means that we have to find the answer for each I really quickly. So which of these can we see, can we process quickly? So get rid of all the i's. This is easy, right? This we can just compute all the n, because this all we need to do for this is just count how many of each I of each number. Right. So this is easy. We can do this. So how do we check if numbers less than equal, how many numbers like don't exist less than I? How do we do this? Well, I mean, we can also pre-compute this, right? So now the problem has turned into like, how do we, for each I, find how many less than I don't exist? And for this, right, if we already have the array that counts how many of each number exists. So then all we have to do is just loop from I. So loop I from 0 to n. Or like let's do probably from I guess probably from 1 to n, because we don't actually need to loop at 0. We loop I from 1 to n, and at each time, right, we see that if I exists, like if CNT, if count I is not equal to 0, then that means that I exists, and that means we add we add 1 to the number of numbers that exist before I, right? And we can just keep looping from I. We just loop on and just pre-compute this whole array. And after we pre-computed the array, we just plug everything back into the original solution, and then all of our queries can be done in linear time, right? Because after we pre-computed it, that means that our comparing two things is linear. So this is a really easy the implementation for this problem is really easy. The problem is pretty much just like 4 lines of code, but you have to be able to like slowly chug through the kind of like different steps and process each one step by step. Does anyone have any questions about this? No? Does this make sense to everyone? If anyone has any questions, just make sure to type in chat. Okay. If that's fine, then we'll keep going then. Actually, I guess it's like, so for this problem was like, I think if I remember correctly, kind of similar to problem 2 of last contest, as in like it's another problem where you just needed like an array and you just need to do operations on an array, right? So whenever you have a problem like this, first try to solve it for the like lesser test cases, right? And then you want to think about like, what can I store that I don't need to like, such that I don't need to redo everything, in step, right? So here clearly, like we saw that looping over the entire array again and again after each step is not going to be efficient. Instead, we can just loop over it once, and we loop over it once, we're able to store things that we can use for every single time. So for example, like number of i's, right? We don't need to loop over it every single time because we can just do it once and it'll still work. And then the numbers of numbers that exist before I, like that's a little harder to think about, but at the same time, like yeah, like you need to be able to realize that like you have to do some kind of pre-computation, and this is going to be something that you just have to start thinking about. Okay, like this is going to be possible. Okay, that's pretty much it for this problem. So I'll just go into problem three, which is probably the most complicated problem. Okay, so this problem, I'll go over the problem statement first. So we basically have the problem statement is kind of confusing. So we have kind of a language. Yeah, like for some problems like this, you don't need to fully understand the entire problem statement, right? Actually, no, you do need. Like, so it's like, no, you do need to understand the full problem statement. So take your time and understand it, because like you have to be able to abstract this problem. Like, even though the problem statement is really long, in reality, it's the problem ends up not being like, yeah, the problem isn't as complicated as the statement makes it out to be. So in general terms, what the problem is asking for is saying that, okay, so we have these operations, so we can either, it's kind of like coding, right? So it's like we have like a loop, right? We can choose to loop over something. We can choose to print, and we can like everything within a loop gets repeated. So yeah, we can do like loop, print, then loop, and then like another print within it. And then each time we need to see if an array is possible to be made using only a certain number of print operations. So when you get a problem like this, you definitely want to you need to always you need to try to do everything by hand first, right? There's no like you have to fully understand like, well, what makes something possible, what makes something not possible. So let's take a look at the samples you got. So sample is one, right? So two, one, one, and then so two is the number of test cases, and then one is yeah. So the first test case is one, one, two, one, one, one. So clearly this is possible, right? Let's think about how we do this. We can just like print one. This is pretty easy. Second operation, we see that second test case is 4, 1, 1, 1, 1, 1. This is also not too bad, right? We see that we only have one print operation, but we can just do like loop 4 times, right? And then print one. That's pretty straightforward too. Let's look at more test cases. So we want to let's see this test case 4, 1, 2, 2, 2. This one, how we do this? So we want to first print one, right? And then loop 3 times and then print 2. And this is in fact doable with only 2 print operations. And I hope you guys are starting to realize, okay, so if we have like a lot of repeated numbers, right? So we have like a lot of numbers in a row, like this is obviously just doable with one print statement, right? And this also applies to, yeah, let's just keep doing test cases, right? Second one, this test case, 4, 2, 1, 1, 2, 1, not really possible, right? Because we have 2 ones and then 2 and then 1. But like we can't, so we'll use one print operation for the 2 ones. We can't join them together with this one. So that means it's kind of not possible. Next one, right? For this case, 1, 1, 2, 2. If we have 2 number operations, it's possible, right? So we loop twice, print 1, and then loop 2 times again, print 2. Right. So that's again, this is again possible. And let's look at a more interesting test case. So this is an interesting test case. So we see that so far we've seen that if we have a bunch of the same numbers over and over again, we can just use a loop to do them all at once. This one's another interesting test case where you have 10, 2, and then 1, 1, 1, 2, 2, 1, 1, 1, 2, 2. So here, right, we see this is possible because we can just loop over this twice, loop twice on the outside, loop 3 times on the inside, print 1, key 1, loop 3 times. I'm going to use LMP, so loop 2 times on the inside, print 2, right? And then this gets us our code. And we see the reason why this is possible is because the first half is equal to the second half, right? So this part is equal to this part. And that means that we can loop twice. Yeah, we can basically treat them as one operation and loop twice to do them. And I hope by now the pattern you guys are noticing is that, so, okay, if we ever have like a segment, right, that's made up of like, let's say a bunch of small chunks that are all equal, let's say 3 chunks, right? we can, the problem just becomes, can we do, like, we don't, yeah, we can process the 3 chunks at once. Basically, yeah, if we can make this 1 chunk, we can do the 3 chunks. So because like, yeah, evidently like we can, if we make this 1 chunk, all we have to do is put like a loop of 3 around it and it'll make this. And this can be done for as many chunks as possible, right? There could be like 5 chunks, right? 5 chunks will still work, right? If all these 5 chunks are equal, if we can just print this one, we can just put a loop 5 around it and do it. And do everything from there. Um okay, so this problem becomes breaking down chunks. Okay. Before going to full solution, let's look into some of the uh partials. Okay, so k equals 1. This should be really easy. So k equals 1. If k equals 1, that means we only get one print statement. So if there's one print statement, that everything has to be equal. So if everything's not equal, we can't do it. That's a very easy solution. K less than or equal to 2. This is a little trickier, but we see that for k less than or equal to 2, we were actually able to do some that means there's only at most 2 numbers, 2 different types of numbers. And that means that we only can like do one number one time. Like if there's okay, so if all numbers are equal, right? So k equals 2. If all k equals 2. If all uh if all equal, just it works, right? So the only operation, so if there's 2 different types of numbers, that means that they have to like be able to be split into various parts. And eventually the like one, like let's just say, so it has to be like 1 and 2. So they're not equal. So if not, have 1 and 2. We see that all the 1s and the 2s must be able to be grouped into a contiguous range eventually. Right. So we have to be able to divide down the original array. Let's say something like this, right? 1, 1, 2, 2, 1, 1, 2, 1, 1, 2, 2. We have to be able to divide it down to the point where, yeah, the 1s and 2s fall into a contiguous range, because otherwise that's not going to be possible. Like, because, yeah, it's like, for example, like 1, 2, 1 is not printable with only 2 print statements, because we have to do print the 1 first, then the 2 first, and the 1 first. But 1, 2, 1, 2 is printable because we see that 1, 2, 1, 2, this half is equal to this half. So this whole segment is just equal to 1, 2. And 1, 2 is a positive statement. Right. So we can do some math on this. And yeah, so I think these two this sample is definitely a lot harder. The 4 to 7 one, no, not sample. This test case, 4 to 7 one is definitely going to be a lot harder. But if you just want to do some math to figure it out, not some math. If you just do some operations to figure it out, you should be possible. Okay. And from these, I hope you guys noticed that basically the number of ways you can divide a segment is just, you can divide it into anything that's going to be a factor of the original number, right? So for example, like if we have like one, if like let's say like n equals 6, right? 1, 2, 1, 2, 1, 2, right? We can try to divide it like this. This doesn't work, but it's like we can still try to divide it like this, right? We can't divide it into 4, right? Because this isn't like even a division. And we can try, so we can try to divide it into like 2 and 3 in this case, and this would work. So we divide into, it would work. So the only numbers we have to test are going to be the numbers that are a factor of the original number. And so this should be able to solve this for k less than 2, because you try to divide everything into like numbers that are factors. And basically, if you can divide them into a number, into a like a substring where it's like only 1s and 2s in a contiguous manner, then it'll be possible. Okay, so now let's go into the full solution. The k equals 3 case, there's like so many different ways to do it. It's going to be really hard. But I think the observation you have to make at this point is this problem is kind of like recursion. So if we have like a problem like this, right? Let's say like 1, 1, 1, 2, 2, 1, 1, 2, 1, 2, 2. This problem recursively breaks down into just this segment, right? Because we saw that. So solving this is the same as solving the original problem. So each time we just want to think about, okay, we want to consider all the possible ways we can break down a problem and turn it into the original. But on top of splitting it like in half like this, right? There's also other ways to split it. For example, because we can also split it. For example, let's give the sample, let's give the test case, let's say like k equals 3, right? If we were given 1, 1, let's see, 1, and then like 1, 2, 1, 2, 1, 2. So this, if k goes like this is like the original problem can't be broken down into like this can't be divided into equal segments. So this one might seem impossible, right? But the issue is we can first print one first, and then we can split it into split it into like three equal segments. So the part that's like the let's say like the program for this problem would be P1, then L3, and then L3, and then P1, P2. And this will be doable with k equals 3. So the recursion states now that break down to into basically we can split the we can either use we can either choose to split the problem the original segment into any two chunks, right? And then but the issue with this is that so these chunks, these two together, have to have the same number of operations as the original one, right? So we can like so in this operation, so this is k equals to 1, k equals 2. And as long as these ones are possible, then we can solve this. And this is the same as solving the original one, right? But alternatively, we can also break down the problem into let's say like let's say we want to this test case, right? K equals 2, 1, 2, 1, 2, 1, 2. We can choose to break it down into an equal segment, right? So we see that these three are equal. So then all we have to do is solve the problem in this case, and k is still equal to 2. So 1, 2, k equals 2, until we get to a base case where either we see that the problem is just not possible, right? So if k equals 1 and it's not all equal, it's not possible. That's a base case. Or we get to the case where all the numbers are equal, then and k is greater than equal to 1, then the problem is possible. So this one does require recursion, so you have to recursively solve this. There's two tests. Yeah, there's two possibilities each time. You either break it in half some way, or you find some segment that can duplicate into the original array, and you can recursively solve on that. For implementation details, I'd recommend write the recursion as like so. We have a solve function, right? I'd recommend passing in L, R, and then K. So L and R are basically segments. It's just like so. The whole problem is like represented as like segments of the original array, right? No matter how we do it, we're always going to get a contiguous segment of the original. So we pass in L and R. So saying that's like, for example, we're passing the start and the end of the segment, and then K is our current like the current number of steps we're allowed to do to try to solve this segment. And then each time, so we either try to break it in half is the first step, and then second one, or find duplicate segment. And duplicate segment means like a segment that can duplicate into the original. Okay. Yeah, and that's the actual implementation details. I don't think I'm allowed to show the code, so yeah, I'll leave it at this. You'll have to figure out how to do this. The next thing, the only other thing I'll do is I'll kind of prove the time complexity. So although the time complexity of this like might seem pretty high because you're recursively breaking into a lot of layers, I think it actually isn't. Because so let's say so we start with the original test case, right? We start with the original case. It can either break down into two steps. So the first step is well, basically, so original is k equals 3. So when you think about this as layers, right? K equals 3. So the only way it can remain as k equals 3 is by duplicating. So this is a duplicate. So duplicate will remain k equals 3, but we'll get a smaller thing. But the other thing about duplicate we notice is that we can only get a duplicate if the number of factors, like if basically it's going to be a factor of the original. So there actually aren't too many ways to duplicate it. There's only like 12 ways. Like the largest number, the most factors that number under 100 have is like 12. So we can't actually, there's only like 12 different times to duplicate it. Theoretically, these can also duplicate other ways, but in reality, like I think this actually doesn't go very deep. So this can maybe go like 2 or 3 times. So this like has like even fewer options. So if we duplicate it once, if we go on one factor, this will probably have like 2. So this will like hop kind of in between the k equals 3 layer. From each layer, we can also go down into small layers. So we can go into like a k equals 2 layer, right? The number of ways to do this is 100 ways. So there's 100 ways to go down because there's 100 like if n equals 100, there's 100 ways to split the array in half and go down to like a k equals 2 layer. Same thing from k equals 2 can also duplicate, right? And each of these also splits to 100 ways. And this would also be 100 ways to undo k equals 1. And k equals 1 is the final state. There's nothing else after that. So we see that the time complexity of this actually isn't that high. It's going to be like some kind of factor of like, so it's like 10 times like, so it's gonna be like, if we follow the troll tree down, it's gonna be like around like 12. It's like some factor of like, 100 times like, probably like 12 times like maybe another 12, and then times 100 times 100. And so you're gonna get some, maybe another 12. So you're gonna get something in the range of like 100, like, yeah, like 10 million, 50 million or so. So overall, the time complexity kind of, it does kind of end up checking out that it won't take too many. But during the actual contest, so theoretically there is a way to reduce the number of the time complexity of this with dynamic programming, because you notice that like the states, the repeat states is just L, R, and K. So technically the number of states total is 100 squared times K. So it's technically only 30,000 states. But at the same time, there's never been DP needed on a bronze contest, so don't worry too. Like, if you come up with a solution like this that seems like it's gonna be running around much time, just code it up and try it. Like when I was coding this, I was like, I think this runs in time. I'm not. I can't. It's kind of hard to rigorously prove, but if I think it runs in time, like, and it's also bronze, so like, I think this is like there's no way it would need DP, and you code it up and it does pass. So like, yeah, if you have a recursive solution like this that seems like it won't like completely explode out everywhere, right? So I'm like, yeah, like this, there's only 3 layers, right? Recursion like exponentially increases with the number of layers there are, but since there's only 3 layers, the kind of like rough estimate is like 10 to 10 cubed. That's kind of like the rough amount of steps are going to be, and 10 cubed does pass. Oh no, not 10, 100 cubed does pass. Yeah. Does anyone have any questions about this problem? If anyone has any questions, type in chat. Is otherwise, yeah, okay. Okay, if there are no questions, then I'll pretty much wrap up this contest. I'll give over some contest, we'll go over some contest like observations I noticed. So the kind of, so I've recognized that like, well, I feel like bronze is getting harder and harder. This contest was definitely harder than yeah, it was definitely harder than the bronze contest last year. But it was around the same difficulty as the bronze contest in January, I think. So as in, and it also kind of followed the same formula of like, it was basically the exact same formula as the January contest. Like A was like some kind of like, it was mostly like implementation. I guess you can add implementation here. It was mostly an implementation problem for A, right? Ad hoc implementation. It was also a grid, just like in January from one, so it was kind of the same thing. Yeah, and the only way to get better at this problem is just code more. Like there's just nothing else to say, right? I think most people like, yeah, like the observations in this problem weren't very tricky. Like you just had to observe that, okay, like every single point has 4 points that can reflect to it back and forth. And so we just have to make sure these 4 points like are all the same, and we have to do the minimal operations. Like yeah, I think that there's not much thinking required in that. It's just like you have to have good, clean implementation. And yeah, the only way to do that is just by practicing solving problems and making sure you build a good like, yeah, way to think about problems in code. Problem 2 is more straight up ad hoc, so it's more yeah, straight up ad hoc is just you have to be able to make the observations. I think problem 2 of last January was also like an array thing. This one is easier though, not gonna lie. But in order to do this, it's just like, okay, so you have to be able to solve, like, try to solve a simple case and then be able to pre-compute. Think about how you can pre-compute to reduce time complexity. So something like this is also kind of just, yeah, you need more practice. Like you have to practice dealing with like, so what you have to think about, okay, what can I pre-compute? What is useful? What stuff is like, yeah, what stuff do I need in this array for it to pass? And yeah, all stuff like that, basically. And there's not much else to it except for practicing more problems. The last problem is definitely harder than most bronze modules I've seen because it requires yeah, recursion. I haven't seen recursion in bronze in a while. So this is the first like actual advanced thing you do. So if you haven't learned recursion before this, yeah, I definitely represent you definitely need to like take some more classes. So I think this stuff is covered in XCamp 200 and 201, stuff like recursion. Yeah, so so if you haven't learned recursion yet, this problem is pretty much impossible to get. But you could have probably gotten the first like 6 test cases for cables too. Those were possible. But yeah, so this was like the first one that actually needed some knowledge and also some more practical knowledge as well, because this needed a little bit of thinking about how to actually implement. I think the cutoff for this contest is gonna be pretty high, like 650 or 700. Pretty low, I mean, like it's gonna be like 650 or 700. So 650 or 700, that means that like actually one and a half, one problem and 2 halves is not completely enough for that. So I don't know. Like I think this was a like problem 2 on this contest was definitely pretty easy. Problem 1 was doable with just code. Problem 3 was pretty hard. So I think your target probably was to just solve 1 and 2. And if you solve 1 and 2, you probably would have passed the contest. Yeah, I don't have too much else to say. I think there's technically 10 minutes left, but yeah, there's no more questions. So if anyone has more questions, I'll stay behind and answer. But otherwise, thank you for coming. And if you pass, good job, or otherwise, good luck on US Open next month. Wrap it up here. You solved the first 2 test cases on the third problem. That should be good. Yeah, I think 2 problems and 1 test case is probably enough. I think the cutoff's probably going to be around 650. I think. Well, I mean, obviously, I don't know exactly, but this was a pretty hard contest.